Yeah, good evening, ma'am.
Participants, it is time to start our next session. We are honored to have Dr. T. Ramakrishnudu sir as our resource person for next session, that is quantum machine learning overview. Till now in the first session, we have seen complete basics of quantum computing. So now we are just moving to the overview of quantum computing with machine learning. So before going to the session, I want to introduce our resource person. Sir Dr. T. Ramakrishnudu sir is an associate professor in the Department of Computer Science and Engineering at the National Institute of Technology, NIT Warangal. With over 15 years of teaching experience, he has a distinguished academic background and significant contributions to the field of data analytics and machine learning. Dr. T. Ramakrishnan sir holds a BTech in Computer Science from JNTU Hyderabad, MTech in Computer Science from Andhra University, and PhD in Computer Science from NIT Warangal. He has published numerous research papers in reputed international conferences and journals, and guided multiple PhD scholars, and actively participated in technical conferences as a program committee member and session chair. Sir is a resource person to many faculty development programs sponsored by UGC, AICT, TechWeb, and many organized by other engineering colleges. He is a member of IEEE Computer Society Technical Committee and ACM and CSI. His research interests include distributed data mining, big data analytics, web mining, and large-scale machine learning. Thank you, sir, for accepting our invitation. On behalf of AVNIT, I welcome you to the session.
Thank you, ma'am. Thanks for the introduction.
You are co-host, sir. Now you can present your screen.
Yeah, thank you. Yeah, is it visible?
Yes, sir.
Okay, thank you. Yeah, good evening to all of you. Um, First of all, I would like to congratulate the organizing team and the host institution for choosing this advanced topic as their FDP, because this quantum related things like the quantum computing and integrating this artificial intelligence and the quantum computing, that is the quantum machine learning, is advanced one. There's a lot of research is going on both at the ends, at pure quantum computing and the machine learning and the integration. So those who are, especially this kind of FDP is much useful for the participants, those who are thinking to do their research in this domain. There's a quantum machine learning, quantum computing, quantum artificial intelligence. So this session is dedicated to give a brief introduction, a overview of this entire quantum machine learning. What it is exactly? What is the need of this? Because we have many systems and the learning algorithms are well established. On top of this, why we need to bridge both the technologies, the quantum computing and the artificial intelligence. So what kind of changes are required when it comes to the data, when it comes to the algorithms, comes to the what is required to to combine, what is required to do these kind of computations in the quantum. So we'll go in detail of this, the entire quantum things. Anyhow, you got the basic details in the previous session. You got the basic details of this quantum computing. What is this? How will represent the system in this case? How the bits are represented, and how the states are represented, how the data is represented before feeding into the models, learning models. So, based on that, we'll continue our session.
Sir, can you please, make slideshow of the document, PPT? It is
Pardon?
not show. It is not showing full screen mode, sir. The PPT.
Is it?
Yes, sir.
Is it okay now? Are you able to see the slide changes?
No, sir.
Really? Is it okay, madam, now?
Yes, sir. It's good.
Are you
Yes, sir.
getting these changes, slide
Yes, sir.
changes?
Yes, sir. Now it's
Okay,
fine.
thank you. Thank
Thank
you.
you.
So this particular FDP, especially this session, assumes that the participants are familiar with the learning things. If not, a simple one slide introduction to that, because it's a combination of both. So learning things are looks like recent things, but it was started long back. It's a simple technique making the computers and application to learn themselves. ML is a common platform which is mingled in all aspects of our life, from the agriculture to the mechanics. So computing is a key component to use machine learning easily and in an effective way. As computing technology growing faster and faster, mathematics entered into this field and makes the solution via computing to the real. So ML is a major barrier is to merge the mathematics and the computing. This is a very simple one. So finally, what we'll do it here in this? Simply, we are going to build a model M. Means you are going to build a function with a set of learning parameters, and you are going to feed the data into that, is going to learn to achieve a particular result. So let us move to the next one. So many of this industry, the current industry, understood that the computing field must have the change from the classical to the quantum. Why? Was a need of this. The data, when you are feeding huge amount of data, very large amount of data into this classical learning algorithms, maybe the classical learning algorithms will fail at one stage to answer this, to process this data. Because to extract interesting patterns from the input data, need to process the entire data. That's why we need a better computing technologies. Then they started working on the quantum computing field. This quantum related things is a very vast syllabus. Many things that exist. I think you got the introduction to that. Especially in the last couple of years, the researchers have been investigating the quantum computers can be used to improve the performance of machine learning algorithms. Because we need the machine learning algorithms in real time manner. That means latency is very low. Immediately we want the output. Once it is captured, some data is captured and the data is sending to the cloud and processing and getting the results back, it takes too much time. But that's not sufficient. We want it immediately. So we need a better computing technologies. That's why the researchers started integrating these two. So quantum computers uses the effects of quantum mechanics, and quantum computers takes the advantage of quantum mechanical effects to solve a certain set of problems faster than the classical computers. So a qubit is a unit of information. How the data is represented in case of this quantum computers, the qubits are used like the bits and bytes in case of the classical systems. What it describes a two-dimensional quantum system. So general state of a qubit is represented by a pair of complex numbers. That's the general representation. So now I'm not going to spend in this the circuits because the circuits were covered and it's a complete the computing related things. So I'm skipping this. So let us move to the quantum algorithms. Those algorithms allows us to process the data. So what purpose these algorithms are used? Let us see what are the quantum algorithms are available, and out of those, a few algorithms are useful for the machine learning purpose. So general search algorithms, reverse search algorithms, it searches unsorted databases. It solves unstructured data search problems, and this is the major, or it's a base for the quantum minimization approach, because this particular routine is used in the quantum minimization. Why the minimization problem is required? Optimization. Need to optimize the data. And another algorithm, the Shor's algorithm, efficiently factorize large integers of the data. And also this algorithm does the combination of quantum Fourier transform and the periodic finding to determine the periodically a function related to the factorization. Quantum Fourier transform algorithm. This particular quantum analog of the discrete Fourier transform operating exponentially the faster. A key subroutine to many of the quantum algorithms, like the Shor's algorithm, used in algorithms for periodic finding and signal processing purpose. The basis for quantum phase estimation algorithm. This is also a part of quantum phase estimation. It is used. This routine is used. It estimates the eigenvalues of unitary operators because it is one of the major one in the quantum machine learning algorithm development. So basis for many algorithms, and another one is HHL algorithm. It solves the linear system of equations and provides exponential speed up to certain problems through this. This is very brief about the algorithms. So variational quantum algorithms. So one of the major algorithm which is used in the machine learning, quantum machine learning, it solves the optimization problems and simulates the quantum systems. Something like this. Variational quantum eigensolver and the quantum approximate optimization algorithm. And another famous algorithm is the amplitude amplification. It generalizes the Grover's algorithm and it enhances the probabilities of finding desired outcomes in the quantum state. It enhances the efficiency of the problem. In this. Let us move to the actual topic. This is a very base or introduction to this. What is this quantum machine learning? This is one of the advanced and rapidly evolving field that combines the quantum computing with the machine learnings. So, using the quantum computing machines are the features of the quantum computing, and with the help of that, solving these problems, or these learning problems, maybe the extraction of few patterns, or need to achieve, or need to optimize. Oh, why to go for this? Because we have well established machine learning algorithms. We need to speed of this, the entire process we need to speed. And the capabilities of handling variety of the data. That's why we need the quantum machine learning. What is this quantum machine learning? It is a combined computing field that combines the quantum computing as what we discussed and the machine learning to create faster, more effective machine learning models. For that purpose, we are, we are moving to this quantum machine learning, and for that purpose, we are going to uh, discuss a few uh, learning algorithms, quantum learning. So let me clarify this. What type of models we are going to develop and what type of data we are going to feed it. This is the very famous representation because if you read any textbook related to this quantum machine learning things, these four boxes, look at this, the type of algorithms we are going to use. One side, horizontally, the type of algorithms. The two types of algorithms. One is the classical algorithm, and another one is quantum algorithms. Right? So this wax, look at the waxes is the data, type of data. Please avoid cross talking. Please some I'm getting some noise from the participants. Please mute yourself. So this type of data have the two. One is quantum and the other one is the classical data. So finally, in this representation, see is C and Q. But this C denotes the classical, whereas Q is the quantum. C is the classical and Q is the quantum one. So what I want to convey it here. How do you bridge this small session is meant for understanding the basics of this bridging both the computing things and the machine learning things. That's the quantum computing and the machine learning things. So this left one, this the leftmost one is a CC coming. So the data you are supplying to the model, learning model, is the classical. And the algorithm you are supplying to this model, supplying to the model or the application, is also a classical one. That is the, the normal machine learning kind of. Data is the classical data and the models are the classical models. With the help of those models, you can extract the patterns. Now let us move to the combination of this quantum side. See here, data is a quantum data, right? Data is the quantum data. Whereas the algorithms are the quantum algorithms. Sorry, classical algorithms. Data is represented by using the quantum representation, and that is supplied to the classical algorithms. But for this one, lot of changes required at the algorithm side to understand the quantum data, its representation. Maybe before doing the actual processing, you need to develop some other additional applications are going to focus on that. Right. Then another one. This is compared to this QC, quantum data and classical algorithms. Focusing on this is a bit comfortable, and developing the models in this a way is easy. What is that? Classical data. The data representation is using classical approach. Then that you can supply to the quantum algorithms. So here, need to design the quantum algorithms. What are those quantum algorithms? Changing the classical algorithms into the quantum. Suppose you want to do a kind of neural network. You want to use this neural network for processing the data, and maybe purpose is the classification kind of, the classifying the data. So this neural network algorithm wants to change to the quantum neural networks. What kind of data these are going to accept? Classical data. Data is the classical. But the algorithm is the QNN algorithm. Neural network is the quantum related. Okay. And anyhow, it's a combination of both the things are the quantum. Data is the quantum and the algorithms, the models are also the quantum things. Then supplying the quantum representation of that data to the quantum models, then easy to understand, then easy to process. Okay. Let us go into this. I hope you understood what type of combinations are possible. You can do your own way. If you're comfortable with the classical data and the quantum algorithms, then you can. Suppose you have the quantum machines with you, okay? Then you can use the quantum computing and quantum algorithms, then the supply the data as the quantum data. To understand this, the quantum systems are required. This, okay. So let us look into the algorithms. What are the algorithms are exist? What are the machine learning algorithms are exist? And its versions in case of quantum. So basically, quantum machine learning algorithms are classified into two. One is supervised quantum machine learning algorithms and unsupervised quantum machine learning algorithms. So this is same as the normal machine learning algorithms, the supervised machine learning algorithms, unsupervised machine learning algorithms. Okay, the purpose is same. What is the purpose of unsupervised? Maybe extracting the patterns from the data without any class labels. From the data, extracting some interesting patterns. Supervised quantum machine learning. So there, like the supervised kind of one, you are supplying the data with the class labels, then parameters trained on the labeled data, then is going to assign a class label to the data. The way of working is same, purpose is same. Okay, let us go into the details of these algorithms. Unsupervised quantum machine learning algorithm. So in the normal traditional, this is a classical machine learning algorithms. These are the popular. If you want to form the clusters, k-means is required, a k-medioid is required. This is another optimization kind of one. What is this? Reducing the data dimensionality. Those are. So when it comes to this quantum related things, a quantum version of k-means, quantum version of k-means, that is the q-k-means. Another one is the quantum version of k-median. Then quantum version of principal component analysis, the QPCA. So what it does, it extracts the principal components from the given data. QBM, this Boltzmann machines data. So it learns the underlying probability distribution of the data, and based on that it works. So let us look at one simple algorithm. So I'm not going to the details of mathematics because this session is not sufficient to go in depth. But let me explain very briefly about this k-means algorithms. Same as the classical k-means, we are going to choose the number of clusters, and the number of clusters are k, and randomly initialize the k centroids. So these are all the centroid values. All are belongs to the data. So same, that initialization process is same. These initializations can be done by any methods using classical um, learning algorithm, because you can use that. Maybe subroutines are this part of this quantum k-means subroutine is that you can use that. Then you are going to do this until convergence is reached. What is this convergence here? This is the major law. main loop. Convergence is reached. How will do this k-means clustering? So we are going to, if the data is this, so initially we are going to form a few clusters based on the centers. So we'll repeat this. What is this? Choosing the centers and assigning the data to this clusters based on the distance functions, distance calculation. Based on that, we are going to assign, repeating this process until no changes in the clusters. Once the changes, once no changes are identified in the previous phase and the current phase, no changes were observed, then we're going to stop the process. That's the convergence, is that same thing. Okay. So what is this loop? Choose the closest cluster centroid. So then the over training examples is this the training data or the training data. For each training sample xi, for each sample, use the quantum subroutine. Look at this, the quantum subroutine dist calculation. This is a function. It calculates the distance between, it calculates the distance between, suppose this is the randomly chosen 4 points, 4 centroids. So function, this is the distance calculation function, it calculates the distance between, suppose there is an object xi or x1, so distance between this to the all other centroids. So that is, each training example use the quantum subroutine distance calculation to calculate the k distances between this and the centroid value, because you need to identify this algorithm, this particular object is belongs to which center, which center. So based on that, you can assign to that. So this one you are repeating for each one. Calculate the centroid for each element, for each distance. Just a minute. Just. What's the name? No. So do it for each centroid one, each element and each centroid, because we want to do it. Then use the quantum subroutine. This is Grover optimization. To choose the index of cluster centroid that minimizes the distance between the training samples and the cluster centroid. Okay. Then that's the calculation. Then the inner loop inside of this, what's happening? Then calculate new cluster centroids. Loop over the cluster j equals to 1 to k and calculate the mu-j, that is new centroid, based on the points assigned to that particular cluster. Calculate the centroid. The mu is this, the calculated mu-j becomes the new centroid or new cluster centroid. So this is calculated for each one. This is the general calculation of this. That one belongs to a particular center and this is an element, and the sum of those values, it belongs to this. Where Cj is the number of training vectors belongs to the cluster J. And Cj is the Cj is the set of these vectors. So sum odd value is the number of vectors and the actual values. So this is the general example of this. For example, let me explain that. Imagine that there are the four training examples belongs to the cluster j equals to 2. This is the second cluster. This is the C2 cluster. 1, 2, 3, 4 are belongs to that. And the new cluster calculated the centroid of that particular cluster using this distance calculation one. So this is the general the distance calculation is this, and this operation is executed on the classical computer. So comfortably can execute that. But the function is here quantum function. So we're going to repeat this inner loop number of times and outer loop number of times until to reach convergence is reached. When the subroutine iterates, the algorithm doesn't change the location of the cluster centroids. It's a mathematically speaking, algorithm converges when for each cluster of these values, the distance between the cluster centroids and the iteration values, generally we'll do it and we'll stop at that particular one. This is very simple and easy and comfortable to understand because it's the same as almost the same as this classical, except the calculations looks like the classical one. So let us move to the other type of algorithms. Quantum um, supervised quantum machine learning algorithms. Yeah, supervised quantum machine learning algorithms. So these are all the SVM is the support vector machine um, is the one. So it's a quantum version is QSVM. Okay. Yes. So this one neural networks is a QNN, and the decision tree, quantum decision tree, and KNN, quantum KNN, QKN. Let us see a simple one like this. Still development is going on, and there are many algorithms that exist, but only the major algorithms have taken, and I'm explaining one simple algorithm. Yeah, let us understand those who are new to the field, even the machine learning, classical neural networks algorithms. So this is the representation of classical neural network. Here we'll find the number of layers. So layers of connected neurons. Okay. So the neurons are these are the connected neurons. And it selects the weights in each layer. So each layer is going to use the set of weights. Those weights are adjusted during training process. Finally, it returns some value. The cost function is minimized. The neurons are represented by activation functions, and with the help of activation function, something like a sigmoid and softmax functions, we are going to get the outputs. So in this diagram, just try to understand this diagram. X1 and X2 are the input vectors. Maybe you have the features, you have the data like this. This is X1 and this is X2. Each one is of size n, and this is the feature 1 and the feature 2, and these are you are supplying to the neural network, your network. So this layer is the input layer. Then finally we'll get the output. That's the output layer. It returns output. The y is output. Okay. Now, hidden layer, number of hidden layers, and this, because it varies the network to network, number of hidden layers, and from one hidden layer to another hidden layer, the parameters are going to update based on the input data. Okay. So these are the W1, W2 are the weights. Based on the weights, you are going to train the model function. Who will supply the weights? Generally, the experts. Or you are going to initialize with some value, later the weights are going to update. So that means how important this feature 1 and how important this feature 2 for me. Based on that, I'm going to assign some weights. Then with the help of a simple activation function, f is the activation function. So this activation function is going to predict the output. That output is supplied to the output function, output um, layer. Okay. So that is the classical algorithm. So you can supply the classical data to that and you can process and get the output of this classical. Okay. Yeah. Now let us focus on the data representation, because I want to supply the quantum data to the classical algorithm, or I want to supply the quantum data to the quantum machines, classical machines and the classical algorithms, and the quantum to the quantum thing. So in this case, the first case where quantum data is applied to this, you need to represent the data. Okay, simple example. Representation of classical data in quantum states. Okay, so classical two-dimensional future vector. This is x is the future. Okay, and the two input parameters x1 and x2. Its transpose is represented. And the label is the y. Y is the label. Representing the classical data as a binary strings. So we'll represent this data, each one like this. So each value is represented like this. What is this? 0, comma 1. This matrix kind of representation. Because in the vector, in this quantum related things, this matrices are represented. So these values a11, a12, a1k, and are these something like I equals to 1 comma 2 and j equals to 1 2 3 4 5 k, because in x, in my feature, in my data, in feature 1, k number of samples are exists. Okay, k number of samples are exists, whereas in the second one is also, because it's the second one, 2 1 2 2 and so on up to k number of exists. Okay, so that's the general representation. Now here y is represented like this: b1, b2, b3 and so on bm, because m number of class labels are exists. Okay, m number of class labels is exists, right? And a feature vector expressed in k bits, and the label could be represented by m bits. There's many number of exists. Okay, the number of bits in that is k, and whereas in the output case m number of bits That's why this vector is represented like this. So let us move. The binary strings translated into k qubits, k qubit states for future vector entries and m qubit states for the label kind of one. So this is the general representation of this. This is the input data in case of quantum representation. X1 is combined like this. X1 is with a 1, 2, 3, and so on. This is the quantum states representation, and this is the another one is the k 21 to 2 to and so on to k. So y is represented like this up to m. This is the general representation of the data we're going to supply to the models. Now this QNN architecture, let us look at that. Quantum neural network. So we're considering, for simplicity, we're considering it here feed forward network. So we're going to supply the input data to the input layer, then the activation function will process it and it produce the output. That means no repetition kind of one. Okay. So we're not going to reuse the parameters which we got, the output parameters we got. So this input layer will accept feature 1, 2, and also the additional bits. Additional. The hidden layer U is the hidden layer. Then output is this based on input values. Also, it produces the features, two features x2 along with the output labels. Output labels. So we're getting the input feature vectors, and the class label related thing as an input to this input data, and the class label data we're getting as an input, and supplying that to the U. That's a hidden layer, and it's going to process and it produce the features as well as the output. So look at this. Actually, U is the arbitrary unitary matrix acting on n qubits, can be represented as this U equals to expression of this entire one. So the k number of things, and here alpha k. So the sorry, theta, this one is sigma k is the polymatrices. This is polymatrices. Where k equals to 1, 2, 3, polymatrices looks like this. Where theta equals to this sigma 1, it's just 2 by 2 identity matrix. Identity matrix. There's a 1, 0, 0, 1 identity matrix. When it equals to 2, this is the matrix. K equals to 2 matrix. Then this is 0 minus I, 0 minus I 0. Whereas the next one is in when k equals to 3, so 1, 0, 0 minus 1. So these values are going to supply to this, and with the help of product of it's a product, we are going to get some data. The parameters is k1 to kn are the trainable parameters which can be obtained minimizing the past prediction. This is one simple example of quantum machine learning algorithms. So two types in unsupervised one and supervised case one, two algorithms we discussed. What are the advantages of these quantum learning algorithms. One is the speed. Quantum machine learning can be faster and more accurate than the traditional machine learning algorithms. That's one. And also accuracy, accurate. Quantum machine learning algorithms can be more accurate than the traditional machine learning algorithms. That is what the researchers observed, and that's why we're all planning to move to the quantum machine learning. And scalability. Quantum machine learning can be more scalable than the traditional machine learning in terms of the data. Suppose you want to scale up the data, because your data is growing, data size is growing because input data is coming continuously from different locations, and you want to apply your learning algorithms on that particular data is a scaled data. When you are using the normal classical learning algorithms, you may not process the classical learning algorithm um, using that data. That's why you need to use this quantum things. Okay, so few more advantages. Resource efficiency. Quantum machine learning algorithms can use resources more efficiently than the traditional one. Comfortably are going to use the full this one. So coming to the data part, data insights. Extracting complete patterns or required patterns, quantum learning can provide insights into the data that would be difficult to uncover with the traditional machine learning. Then coming to the optimization. Quantum algorithms can solve the optimization problems more efficiently than the traditional traditional algorithms. What are the you found the challenges, you understood the data representation and supplying the data to the models, and the models how to model it and how to implement that we'll see at the end. Now the question is here, what kind of challenges you are going to face with this quantum machine learning? Suppose you want to develop the quantum algorithms, what is a major problem? These are classified into the different types. One is the hardware limitations. In hardware limitations, one is noisy intermediate scale quantum devices. The current quantum computers have a limited number of qubits, and those are prone to the noise and the errors. So major challenge is improving this number of qubits and addressing noise related things. Okay, decoherence short qubit lifetimes restrict the complexity and the depth of quantum circuits when you are building the circuits using these different things. And the scalability, build a large fault tolerant quantum systems is still undergoing research. This is ongoing research. That's what those who are looking to do some research, or those who are new to this, wants to do the research in this particular field, you can choose this as your research problem. Fault tolerant quantum systems towards machine learning, because it's going. So error rates, higher error rates in gate operations, these quantum gates operations, not gate and other gates, different gates are exist, right? So when you are using those gates, there's a higher error rates in that the gate. transactions. Okay, the next one, data encoding challenge. Why to encode? You have the classical data, you want to shift to the quantum data, then you want to supply that quantum data as an input to your data conversion. This you want to supply this data as an input to your model. Okay. Yeah. Now in this conversion is the one major challenge. Efficiently encode large scale classical data sets into quantum states is computationally expansive. You can work on this also. This is also a open research problem. What is that? You want to develop an efficient quantum classical to quantum conversion, this data conversion techniques. Okay. Encoding methods like the amplitude or the angle encoding requires the significant resources, significant resources may negate quantum advantages. This is the one of the challenge. And the data representation represent the high dimensional data, not only the two dimensions. Suppose the number of dimensions are increased. How to represent that? And the structured data in quantum states without distortion um, remains difficult. So one challenge at the data level, one challenge at the hardware level, and another challenge is at the algorithm level. What kind of algorithms required? Algorithms, there's a problem specific algorithms. Many quantum machine learning algorithms are tailored to specific types of problems or data sets. Sometimes we'll change the architecture, that's the entire state inside the gates and its representation for a particular problem or what type of data set is available based on the data set. So what you are going to limit? Generalizability. Okay. Then hybrid complexity. A hybrid kind of model develop. What is that a hybrid? Quantum classical hybrid combination. Most quantum machine learning algorithms implementations are the hybrid kind of one. So you need the hybrid. You can develop an efficient one. The balance between the quantum and the classical components often requires for fine tuning and remains the problem dependent. So that's balance both the parameters. Then designing algorithms by balancing that. And another thing is missing at the quantum machine learnings is the robustness. Quantum algorithms are sensitive to small changes in input parameters or hardware noise. Something is changed, something is missing, then automatically it affects on that. Okay, that's why what you need to develop robust algorithms. You need to so this is also a research problem. Design of a robust
లైట్ బంద్ చేస్తారు చిన్న లైట్ కూడా వేయాలి ఇప్పుడు ఐస్ క్లోజ్ చేస్తుంది
quantum machine learning algorithms. Okay, so let's move to the another challenge. Error correction. The quantum error correction, so QEC techniques demand a large number of additional qubits. Number of qubits which are required for the data and also there's an output in case of input data and the error correction purpose. So also it expects the computational resources, extra computation automatically, because when the number of bits are increased. The infeasibility is that fully error corrected quantum systems are far from the realization, and limiting the utility of this quantum machine learning and current hardware. Understanding the quantum output interpretability and the debugging. The output of this. So we discussed that input data and the machine's side, then the output. That output is not interpretable. That should be done. That should be interpretable. Quantum algorithms often produce probabilistic outputs, making it harder to interpret results compared to the classical machines. That's why you need to develop some approaches or algorithms at the output level that development is going to minimize the difficulty, and it's going to increase the um, effectiveness and its uses. And debugging, diagnosing errors in the quantum circuits after development of the circuits for the particular problems, because the problem oriented is a challenging due to the lack of direct access to the quantum states. Okay, so if you're able to access the quantum states directly, maybe it's possible, but because of its design, that's one of the challenge. So another challenge is the resource requirements. What are the resources required? Memory and the qubits to scale up. For large scale quantum machine learning algorithms may require more qubits or more than currently available. And computational overhead, encoding the data, this is a data encoding and measurement, then post processing steps can exceed in the potential speed. That means it takes more. And another one challenge is lack of standardized frameworks. Those frameworks allows, because with multiple libraries and algorithms, allows us comfortably use and develop the things. So one is the software ecosystem. While frameworks like the Qskit and Penny Lane, these are the popular, Circ, Exit, they are still evolving. Lot of changes are happening at these software modules or the software frameworks. Okay, and a universal standard for this is lacking. There is no universal standard for the quantum machine learning. That is another challenge. All the researchers are working on that. Algorithm libraries, fewer pre-built algorithms and the tools exist for this compared to the classical machine learning frameworks like the TensorFlow and the PyTorch are popular frameworks and the libraries. Comfortably, you can use and model the data and extract the interesting patterns from that. Like that, we need well-established libraries are required. Another challenge is ethical, social challenges. Accessibility is the one. Quantum computing resources are concentrate concentrated in a few organizations. This is limiting the broader participation in the QML research. Okay, and the bias in the quantum data. If the quantum enhanced data sets are biased, then the model trained and the biased data, then it's going to produce the output as the biased one. Then performance benchmarks is another challenge. Quantum versus this classical one, demonstrating the clear quantum advantages for this. The quantum machine learning task is a challenging one, especially given optimized classical algorithms and the hardware. So many quantum algorithms provide the theoretical speed ups, but may not surpass this classical methods in practice. When it comes to the practical, not that much. Okay. And another major challenge is the scalability. It is it's difficult to benchmark the QML algorithms for large scale problems due to the hardware problems, hardware constraints. Hardware is limited, and due to that, you may not um, achieve that. So these are the challenges we need to. So you consider all the new researchers, young researchers, you can consider the challenges as an input. You can build your research problem based on this. So what are the applications? When it comes to the applications, the same as the applications what you learn and you discussed, the same similar kind of something like the financial things and the medical things, then the language related, image related, cryptography kind of. Then coming to the future trends of this quantum machine learning. So where you need to focus, initially focus on this, or you can focus on this one and develop new models. Those are the hybrid model development. Hybrid is the combination of quantum and classical models. Then you can um, this is the one trend, and many of the researchers are working on that. So, combining the quantum computing for computational intensive tasks like the kernel evaluation, the optimization, with the classical machine learning principles for data preparation and the interpretation. So, data output interpretation, the data pre-processing kind of one you can use by using this, and then you can combine with the quantum related. Quantum data increasing exploration of data sets natively quantum in the nature, such as the quantum states and the um, molecular data and the quantum systems simulations. These are all. And the quantum feature maps encoding the classical data into the quantum states for richer representations and the more powerful feature extractions. So these are the some and uh, few more trends. Efficient data encoding techniques. So we need a better techniques. Using those techniques, comfortably can convert the data into um, the classical data into the this quantum data, or combining the systems. So integration is very comfortable if you have a good encoding techniques. So integration with the classical systems. And the quantum generative models, um, because many researchers are working on this generative models. We know that the generative models importance, what does it, what kind of generations it does, um, text to text and text to image, image to text and image to image, and it's all combinations. So leveraging the quantum systems for the generative tasks, that is the another future of this, and a vision for the QML in the next decade. Vision for that, vision next. So these are the some of the future directions, and you can work on that. So let us look at the programming languages tools for the quantum machine learning. So quantum programming languages and frameworks that combine the quantum computing with the classical machine learning techniques. Okay, right? Programming languages, quantum programming language and frameworks that combines the quantum computing things and the classical learning things. So one of the one this framework is a Python based frameworks. Actually, there are many Python based frameworks, multiple. frameworks supports this one. So Python is the dominant language for this, the quantum machine learning development, because of its simplicity and extensive library ecosystem. So most quantum frameworks are the this are Python compatible. That means comfortably you can develop the routines in the Python, and you can integrate those routines with the Python. This actual quantum related things. So let us look at the few programming languages, the tools, frameworks which are used for development. One is the QSkit. It is a Python library for building and simulating the quantum circuits. If you want to build the quantum circuits or you want to simulate the quantum circuits, you can use modules like QSkit. Machine learning provide tools for QML tasks such as the quantum classifiers, quantum neural networks. These are all. And it works with the IBM quantum hardware and the simulators because it's developed by the IBM, and comfortable it works with the IBM hardware and the simulators. Pennylen is Python library for hybrid quantum classical machine learning kind of. It's a hybrid one, the quantum and the classical machine learning kind of. Supports the automatic differentiation of quantum circuits and also compatible with the multiple quantum benchmarks like the QSkit and the circuit and the other kind of one. And the classical ML libraries like this because it's compatible with both the Python and the quantum machine, quantum computing. And the circuit is the Python library for designing and simulating the quantum circuits. It supports the quantum machine learning via integration with TensorFlow Quantum. Okay. So the actual TensorFlow is the Python library for the normal classical algorithms, and its implementation representation, whereas this TensorFlow Quantum is the hybrid. TensorFlow Quantum, extension of TensorFlow for quantum machine learning. This quantum machine learning. This so extension of the TensorFlow. It provides the tools to combine the classical ML models with the quantum computations. So comfortably using that you can develop. In addition to that, the few more Q hash. This Q hash is the domain specific language for quantum computing. It integrates the Microsoft Quantum Development Kit and supports the classical quantum hybrid workflows with Python and the .NET special representation. Silk is the high-level quantum programming language designed for better readability and fewer low-level errors. Example is automatic computations. And a functional programming language tailored for the quantum computing that focus the high-level abstractions, and OpenQASM is a low-level language for the quantum circuit definitions that and compatible with the quantum hardwares like the uh, IBM quantum processors. And Project Q is a Python compatible quantum programming framework, and it supports the quantum circuits simulation and integration with the quantum workflows. Then Strawberry Fields. This particular framework or library is a Python library for continuous variable quantum computing. It includes the tools for quantum machine learning and particularly infotech. Okay. So let us compare all this at one place. QSkit, these are the popular tools and languages. QSkit, Pennyline, and SITQ, and TensorFlow Quantum, QAsh, SilkQ, and the Strawberry. So this QSkit is the quantum circuit design primary use for the machine learning, quantum machine learning purpose. And the strengths are this versatile and the Python based one, because the many of the users are Python comfortable with the Python. That's the another strength. And the use, then the limitations, it requires the IBM hardware for execution. But it, even though you developed your algorithm by using some frameworks, but execution is possible only, execution is possible only with the this is the limitation. And Penny Lane is the hybrid quantum machine learning tool, and it is used for the primary use of that is developing this variational algorithms. So variational algorithm implementation is very much needed in case of quantum machine learning algorithms. And yeah, and its strengths are the ML integration. Machine learning libraries are integrated with this, and multi backend support is exists for this one. But the limitation is this Q device focused, because it's based on the particular one only it's allowed. And the circuit is the quantum circuits or TensorFlow quantum um, implementation purpose, and its strength is the optimized for NISQ and TFQ integration. And limitation is limited to Google's ecosystem, because when you are trying to implement beyond the Google, it's, you may find the less support for that. The quantum TensorFlow quantum is a hybrid quantum machine learning model, and its strengths is the deep learning and the quantum integration. So comfortably you can implement and execute your deep learning algorithms with a combination of this quantum representation in the quantum computing. Complex setup for the classical quantum workflows is the a limitation, because that is not exists. And the QAsh is the quantum algorithm development, and it is strong for QDK ecosystem, and less flexibility for QML specific tasks. Suppose you are looking for specific tasks. And the Silk is a high level quantum programming language, and it is easy to use and easy to debug, and the limited adoption to the multiple applications and the tasks. Strawberry fields is a continuous variable quantum machine learning algorithm. Its a purpose is primary purpose is that, and the photonic quantum computing focus is the strength, and niche domain is that's another limitation. So these are the few programming tools which are exist, and its a limitation, the strengths, and how to use and what kind of hardware support is required. Based on that, you can develop your own um, quantum machine learning representation. So, any questions? I hope what I plan for this small session is a just brief introduction to the quantum machine learning algorithms, quantum machine learning. So, we started with the uh, algorithms and the data representation, and what are the advantages and what are the challenges involved in development, and types of quantum machine learning algorithms, and a few algorithms in each. I discussed one algorithm in this unsupervised case, the supervised case, and how to represent that. So especially you need to understand the CC, CQ, QCQQ, classical data, classical algorithms, implementation in the classical, execution in the classical machines. Classical data, quantum, what is this, algorithm? So execution of that in the quantum systems, and another one is quantum data, classical algorithms. You can execute the classical algorithms in the classical machines if supports quantum data. Quantum one is the quantum data, quantum algorithms. You need quantum hardware to execute quantum algorithms and the quantum data. So this is the very brief one. This is not sufficient. So you can choose what are the challenges I mentioned. You can choose any one challenge and dig into that, focus on that, then continue your research on that.
Thank you so much, sir. It is very
Yeah, these are the
enlightening.
references.
Yeah, we got the basic foundation for converging both the machine learning and quantum computation. So it was very enlightening to all the participants. Despite of your busy schedule, you have accepted and given the time. Thank you so much, sir.
Thank you, ma'am. Thank you. I'm closing because I have to rush to
Yes,
the
sir.
railway
Yes, sir. I
station now.
understood.
Yeah, yeah.
Participants, please, I will answer your questions personally. I will take the sir opinion, I mean answers, and I will share to you. Because of travel, even though travel is there, sir is attended the session. So thank you so much, sir.
Thank you. I'm closing.
All the participants, thank you so much for joining the session today. Uh, I will be sharing the feedback link once again. Just a second. Please provide the feedback for the session. I will end the meeting. Thank you so much.